Now reaction at A will be 6.25, so it will rise by 6.25 kilonewtons. So this is the rise, let's say this is the rise, and it will continue to be 6.25 kilonewtons up till the point B, and from the point B onwards it is going to drop. So this is 6.25 kilonewtons, and from here it is going to drop to -10, that is making the net shear force as 3.75 kilonewtons. And this 3.75 kilonewtons will be continued up till point C, and from point C onwards again this is going to have sudden drop. So now it is going to have the sudden drop by 15 units extra. So this was 3.75, and at C to D that is continued to be maintained. And let me just extend this support line so that the shear force is streamlined exactly. So and this increases to 8 kilonewtons at D because of the reaction RD. It increases to 8 kilonewtons. And this continues to be maintained up till point E. So this line will be extended up till point E. And at point E, once again, it is going to have sudden drop to 0 kilonewtons. This would be the shear force diagram for the overhanging beam, and this was at D we were getting the value as minus 15.75 kilonewtons, and this would be 8 kilonewtons. This is positive, this would be negative, and this would be positive. So we are finding the transition in shear force two times happening in the overhanging beam. With single overhang it has got single overhang. Next is bending moment at A will be equal to RA into 0, that's 0. Bending moment at B will be equal to RA into perpendicular distance is 3 meters. So RA here it is equal to 6.25. So 6.25 into 3, which is 18.75 kilonewtons meters. Bending moment at C will be equal to, that is RA into perpendicular distance would be 6, that is RA into 6 minus the other load we have is 10 into 3, so 10 into 3 it is, so RA is 6.25 into 6 minus 30 it would be, so 36 plus 0.25 into 6, So 0.25 into 6 is 1.5. So this becomes 37.5 minus 30, which is equal to 7.5 kilonewton meter. That's the bending moment at point C. Next is bending moment at D. Bending moment at D, again you find it over there, the transition happening. So bending moment at D will be RA into the perpendicular distance up till D is 8 meters. So RA into 8 minus 10 into perpendicular distance for 10 kilonewton is 3 plus 2, that's 5, minus 12 kilonewton, and perpendicular distance for that is 2 meters. So RA is 6.25, 6.25 into 8, 6 8s 48, 48 plus 0.25 into 8 it is. So 0.25 into 8 is 2. So this is 50 minus 50 minus 24. That's equal to minus 24 kilonewton meter. That is bending moment at point D. So what is that we observe? We observe that there is a sign transition from positive to negative in the BM diagram or BM values. So bending moment at E, which is free end, this will be 0. So RA into perpendicular distance is 11, total span is 11, minus 10 into the perpendicular distance from B to E is 11 minus 3, which is 8. So 10 into 8 minus 12 into perpendicular distance is 2 plus 3, that's 5, minus RD. RD we have got it as 23.75 and perpendicular distance is 3. So if we solve for this, this is 6.25 into 11 minus 80 minus 60, and this is 23.75 into 3, that is 23 3s is 69, 69 plus 2.25, so 69 plus 2 is 71, 71.25, and this is 6 11s is 66, 66 plus 0.25 by 0.25 into 11 is 2.75, 2.75. So that's 66 plus 2.75, which is 68.75 minus 80 minus 60 minus 71.25. So here if we try to solve, so this is, let me just check. So this comes out to be as 0 kilonewton meter. So bending moment at the free end is 0. So you can justify your calculation. So remember that always try to prove that it is equal to 0, because examiner will be evaluating your understanding based on the calculated values obtained. So bending moment here at A it is 0, and at B it is going to be linear, that is straight line behavior it is. And let me just draw. It's going to be a straight line like this. This behavior will be up till point B, and from B onwards we are finding the change in shear force, that is the shear force is having a sudden drop, and that sudden drop should be highlighted with some discontinuity. So bending moment at B we have got it as 18 point, yeah, at B it was 18.75, and at C it is 7.5. So it is going to drop. It is going to drop at point B. It will be the lesser one. So this is this is C point. So let me just join here. So this is bending moment at C, and let me take this back. This is bending moment at point C, which is 7.5 kilonewton meter. At B it was 18.75 kilonewton meter. Same way, bending moment at D is minus 24. So at D, this is the line which is measuring the SF at D. Let me extend this line further, and I have to mark 24 kilonewton meter on that line. So you can see the line is not continuous. It has got different slope. Let's say this is 24 kilonewton, and let me highlight it with a different color, and let me take this line back. This is bending moment at D, and finally at E point the bending moment is becoming 0. This comes out to be as 0. So this will be the BM diagram. So all you have, whenever there is a point load introduced, that is going to cause some discontinuity. So here, this point where we find the transition in bending moment, this is called as point of contraflexure. Let us call it as F. So F here will be called as point of contraflexure. What is contraflexure? Let's try to understand. So here, if you go back to the loading diagram, and due to the load E, the bending moment is, or the beam is going to take a deflection like this, and there will be a, again, due to support, there will be change. And here, after once we cross the support due to 12 kilonewtons, the bending moment or the beam is going to take a shape like this, or this will be the deformation shape of the beam. So now here you find the radius of curvature. The radius of curvature is directed like this, and here for the from the point D onwards, the radius of curvature is reversed. It is taken from the reverse direction. So whenever you find this, whenever you find the integration, or whenever you find the blending of these surfaces which are convex and concave, so wherever they intersect, that point we would be getting, or wherever they intersect approximately, that would help us locate the point of contraflexure. Or whenever you find a wave kind of a deformation, you are finding a wave kind of deformation, there the point of contraflexure is definitely going to exist. So if you want to mark it, so from point E, the bending moment at E it is 0, at D it is negative, and at C it is becoming positive, which means between D and C the point of contraflexure is likely to exist. So what we can do is we can draw a section like this, and after drawing a section XX or section 11, you could consider the forces which are on the right hand side or on the left hand side. So if you consider the forces on left hand side, it has got RA, 10 and 20. So three terms you have to write. But if you consider the right hand side, it's 8 kilonewton and RD only. So this is quite easier to solve as we have got less number to deal with. So the answer will be same whatever the side you consider the forces. So if we take the bending moment about the section 1 equal to, that would be 8 into x, 8 into x, or this is minus 8 into x, and RD is producing counterclockwise movement, so that's plus RD is 23.75 into x minus the perpendicular distance is x minus 3, it is x minus 3, so that is 23.75 into x minus 3. This should be equated to 0. This is minus 8x plus 23.75 x, and this is 23 3s is 69 plus 2.25, that is 71.25. this is equal to 0. So here 18 minus 8 minus 23 is 15. 15.75 x minus 71.25 is equal to 0. So x is equal to 71.25 divided by 15.75 it would be. So if we calculate this, so x comes out as 4.523 meters. But here in the question they are asking the point of contraflexion, and if we consider from B, from the point D, okay, this is from E, actually this is measured from E. So if it is to be measured from D, from point D it is, then it becomes 4.523 minus 3 it is, which is 1.523 meters would be the location of point of contraflexion. So point of contraflexion is going to tell us the change in the direction of bending or change in the direction of radius of curvature. In the question, it says about a cantilever beam whose span is 2 meters. It carries a point load of 1 kilonewton at the free end and the other load of 2 kilonewton at a distance of 1 meter. So this is 1 meter and this will be 1 meter. For this situation, the shear force and bending moment diagram is to be drawn. So let's name the point. The fixed point is A and the point where 2 kilonewton is placed will be B and this will be C. So first is that we calculate the reaction forces. So that's summation of forces in y direction should be equal to 0. At the fixed end, there will be a vertical reaction as well as there will be also a reactive moment. So summation of forces in y direction, that is Ra minus 2 minus 1 equal to 0. So Ra will be equal to 3 kilonewtons. Next is computation of moments. So minus that is moments about point A is equated to 0. At point A we are finding a concentrated reactive moment that needs to be added. So minus Ma plus 2 kilonewton will produce clockwise movement about A. So 2 into perpendicular distance is 1 plus 1 into perpendicular distance is 2 for the point C. So this is equated to 0 and Ma becomes as equal to 4 kilonewton meter. So this was the computation of reactions at these supports. Next is we go into the calculation of shear force and bending moment. So shear force at A will be strictly equal to Ra only. That's 3 kilonewtons. Same way, shear force at B will be, it's still Ra, that's 3 kilonewtons, and at B we are finding a point load of 2 kilonewtons. So because of that, there will be a sudden drop in it. So suddenly changes to 3 minus 2 was the no force. So 3 minus 2, which is equal to 1 kilonewton. And shear force at C will be 1 kilonewton. And at point C, there is a point load of 1 kilonewton present. So because of that, there will be once again sudden drop. So that causes suddenly changes to 1 minus 1, which is equal to 0. So if we plot the SFD diagram for this situation, then the diagram is expected to be like this. So let me just align this line. So at point A, the shear force is 3 kilonewtons. So it continues to remain constant at point A. Up till B, it is continuing. So let me just draw the SFD diagram with reference to the loading. So I need to extend it. This was point B. So this is 3 kilonewtons. Next, from point B onwards, there will be sudden drop in the shear force, that is of 2 kilonewtons. The drop is going to be. And from point B onwards, again, the shear force is going to remain 1 kilonewton. And same way, at point C onwards, at point C, we will be finding once again the same sudden drop. So this was the SFD diagram. This is point A, B, and C. And all the shear forces are positive. Next is computation of BMD, that is bending moment at A will be equal to minus MA, which is minus 4 kilonewtons. Next, bending moment at B will be minus MA plus RA into the perpendicular distance between A and B is 1 meter. So that is 1. So minus 4 plus 3 into 1, which is minus 1 kilonewton meter. Same way, if we compute the bending moment at C, it will be minus MA, that is 4, or let me write it in terms of minus MA plus RA. How RA is far from the point C? It's 2 meters. So RA into 2 minus about point C, the 2 kilonewton will produce anti-clockwise movement. So minus 2 into 1, minus 2 into 1 it is. So MA is minus 4, RA is 3, 3 into 2 minus 2, which is equal to 0. So bending moment at C point will be 0. C is referred as fixed free end. C is referred as free end. So at the free end, the bending moment will be 0. So let's draw the BMD diagram. This would be point A. From A to B, it is from A it is at A it is 4 kilonewton, at B it is becoming as minus 1 kilonewton meter. So I need to join this by using a straight line. Let me use another color. So this is point B. I need to erase it off. And at point C, once again, the bending moment will be there. But do remember, dear students, that this line will not be continuous. This line will never be continuous. From B onwards, the line is going to have a different slope. So to highlight that, let me use a different color. So you can see here the discontinuity is been reflected. One is indicated by red color line. So although you find some variation between these two lines, so that is the purpose to highlight the discontinuity. As you find the 3 kilonewton is not continuous, and that same thing is also will be reflected in the BM diagram as well. Okay, so let me use a different color in order to give you a contrast. So this will be bending moment diagram. So this is going to be negative. At A it was 4 kilonewton meter. At B it is 1 kilonewton meter, and at C it will be 0. So why is that it is becoming discontinuous? There is a mathematical proof for it. So we can write it. As far as the diploma level is concerned, you can avoid writing this, and if you have understood the concept. But in the undergraduate level, you would be needing this, or you should learn this technique of writing. So let's say this is section XX placed at a distance X. So this is, and at this section, if I take the moment about section XX, let's call this as section 11. So this is moment about section XX, which is on the left side of the section, we find a anti-clockwise movement, that's minus MA plus RA into X it is. So minus MA is 4 and RA is 3. So minus 4 plus 3x it would be. So this will be minus 4 is indicating negative y-intercept, and 3 is the slope of this line, the red color line. Now, once again, if I place the section between the points B and C, what do I get? So once again, this distance will be marked as X only, but let me write this section as 2, 2. So moment about section 2, 2, if I write, this will be minus MA plus RA into X. It will be copied as it is. There will be additional term when we are shifting between points B and C. That additional term is 2 kilonewtons, and 2 kilonewtons about section is going to produce anti-clockwise movement. So that's 2 into the perpendicular distance between 2 kilonewton and section X axis, X minus 1 it is. This distance would be X minus 1. Up till the section, the distance is X, and 2 meters or 2 kilonewton is at a distance of 1 meter from point A. So the distance would be X minus 1. Now, if we simplify this, minus MA is minus 4 plus 3X minus 2 plus 2 it would be. So this will be minus 4 plus 2 is minus 2. Minus 3 minus 2 is plus. My 3x minus 2x is actually x. So we are finding here the change in slope. Earlier there was 3x was the slope, 3 was the slope, and now 1 is becoming the slope. So you don't have to be very accurate in highlighting about increasing or decreasing the slope, but you should be able to highlight the discontinuity. Okay, that's really very, very important. So you can learn this habit of writing the section XX, but at the diploma level, once again I said, it's not that much advisable if you have understood the concept of highlighting the discontinuity. That can be avoided, because this technique of writing the section XX we will be seeing in undergraduate syllabus, as well as when we do the concept of slope and deflection. Even then it is needed to be learned. In the question, it says about a cantilever beam whose length is 2 meters. It carries a uniformly distributed load whose value is 2 kilonewton, 2 kilonewton per meter, and the entire span, and there is a point load of 3 kilonewton is applied at the free end. It is required to be developed. In the question, it says about a cantilever beam whose span is 2 meters and it is carrying a uniformly distributed load of 2 kilonewton per meter over an entire span, and there is a point load of 3 kilonewton at the free end. And for this situation, the shear force and bending moment diagrams are required to be developed. So let me just write the span. The span is 2 meters and the height of UDL is 2 kilonewton per meter, and there is a point load acting at the free end as well. So first is that we commence with calculating the unknowns, that is reactive force RA. Let's call this point as A and let's call this point as B. So there will be reactive force RA and there will be moment MA in anti-clockwise sense. So summation of forces in y direction, that's equal to 0 RA minus the area under UDL, that is 2 into 2 minus point load is 3. This is equal to 0. So RA will be equal to 4 minus 4 minus 3, that's minus 7 kilonewton. And same way we can calculate moments about A is equal to 0. At A we find a concentrated reactive moment that is in anti-clockwise, so minus MA we write it as. Later, next, the UDL is converted into force, that is 2 into 2, and the midpoint, this UDL is going to act, or the point, if we convert the UDL into point load, it will be 4 kilonewton, and it is going to act at the mid of this span, that is 2 by 2, which is 1 meter. Okay, so let me just write it over here. So 2 into 2 into 2 by 2 plus, next would be 3 is at a distance of 2 meters from point A, and 3 kilonewton is going to produce clockwise movement. Even UDL produces the same kind of movement, that's in clockwise. So this is equal to 0. So MA will be equal to 2 to 4, 4 plus 6 it is, that is 10 kilonewton meter will be the bending moment. Next is we commence with computation of shear force. So shear force at point A will be straight away equal to RA, that is 7 kilonewtons. Now shear force at section XX, if we consider, let me just draw the section XX over here. So we are placing a section XX at a distance of x from the point A, and shear force at XX can be written as, once we go to the section XX, we find RA force, and along with that UDL is distributed over a span of x meters. So RA, that is 7 minus UDL, height of UDL is 2 times of x it would be. So the equation of shear force is 7 minus 2x, and shear force at B will be equal to, that is we need to substitute x as 2 meters. So SF at B is equal to 7 minus 2 into 2, which is 3 kilonewtons. And at the point B, there is a concentrated load. So due to the concentrated load, the shear force suddenly changes to 3 minus 3, which is equal to 0. So let's draw the shear force diagram. So here, first is that, yeah, this would be the base of the shear force. So now here the height of shear force at point A will be maximum, or that is going to be 7 kilonewton. So let me just extend it. This will be 7 kilonewton at point A, and at from this point you will be finding the shear force is going to decrease. How I can tell that? If you check the shear force equation, in that you find 7 minus 2 times of x. This is analogous to c minus mx, that is y is equal to c minus mx. So minus 2 is nothing but it is indicating the decreasing slope. So here onwards we will have decreasing slope up till the point B, but it will not be 0. And at B we will find the sudden transition in the shear force, and then it becomes 0. So from 7 up till point B it decreases to 3 kilonewtons, and at point B we are finding the point load or concentrated load. Due to this concentrated load, there will be sudden drop in the shear force. So this will be positive, and this will be SFD diagram. SFD I should say. Next is bending moment calculations. So bending moment at point A, that is BM at point A, that is straight away equal to minus MA concentrated moment. So that's minus 10 kilonewton meter. Same way, bending moment at section XX if we consider, then this is bending moment at XX location. Here on the left hand side of the section we find a concentrated load RA, or in the form of reaction. There is a couple MA in the counterclockwise, that's with the negative sign, and some portion of UDL over a x meters length. So how do we write? First is we begin with minus MA. Next is RA. How far RA is from section XX? It is at a distance of x from the section XX. This would be the section XX. So it is at a distance of x meters. X is a variable which is going to have values between 0, this is 0, and this is 2 meters. So x is a variable, and this section XX is written, bending moment about section XX as well as shear force about section XX is been written to understand the variation of SF and BM along the length of the span. So in the SF we found out it is x power 1 behavior. It's a straight line. It's a straight line, and for bending moment we need to calculate. So minus MA plus RA into x, and UDL will produce anti-clockwise movement. This UDL will produce anti-clockwise movement about the section. That is, height of UDL is 2. It is distributed over x meters of length into centroid of that is x by 2. So here minus MA is 10, minus 10 plus RA is 7, minus 10 plus 7 minus 2 and 2 will get cancelled. This will be x square. So this will be bending moment at section XX, and bending moment at point B if we are required to calculate. So that is going to give us x equal to 2 meters. And if we substitute x equal to 2 meters, that is minus 10 plus 7 into 2 minus 2 square it would be. So this is minus 10 plus 14 minus 4, which is equal to 0. So bending moment at point B will be 0. Let me just draw the BMD diagram. So in the BMD diagram you will be finding the bending moment at A location. It will be maximum, that is 10 kilonewton meter. And from this point onwards up till the point B, there will be parabolic second degree parabola variation. So the variation would be like this. This is a second degree parabola, that is x square. So please remember that whenever you find a UDL, so UDL is a horizontal line. The horizontal line is represented with x power 0 behavior, and SFD is represented with x power 1. So you can see here x power 0, x power 1 and x power 2. That pattern follows as we keep on computing the parameters. So this is one way of recognizing or analyzing the patterns hidden in this SFD and BMD, and whatever the case you consider, whether it is a cantilever beam or simply supported beam, the same situation follows. So in the question, it says about a simply supported beam whose length is 8 meters and carries 2 point loads. One of them is 24 kilonewtons and the other one is 40 kilonewtons at a distances of 2 meter from each of the ends. So this is 2 meter and this is 2 meters, and the distance between both the loads is 4 meters. And for this situation, the shear force and bending moment diagram needs to be drawn. So first is that we calculate the reaction forces. Let me call this as RA in y direction and RB. So first it commences with the equilibrium of forces, that is RA plus RB is equal to the downward forces 24 plus 40. So this is equal to 64 kilonewtons. Next is the moments about the point A. So 24 kilonewton produces clockwise movement about A, that's 24 into 2, plus 40 kilonewton produces clockwise movement about the point A as well. So that is 40 into 6 minus RB into the distance between A and B is 8 meters. This is equal to 0. So RB will be equal to 48 plus 240 divided by 8 it is. So this will be 288 divided by 8. So this is 8, or this is 2 fours, and this is 2 144s. This is 4 ones. This is 4 3's 12 and 4 6 24. So this is 36 kilonewtons RB, and RA will be equal to 64 minus 36 kilonewtons. So this is equal to 28 kilonewtons. So here we find the 40 kilonewton point load is nearer to RB. So that signifies that RB will be greater than RA. So the higher point load nearer to that support will give us the maximum value of the reaction force. So next is shear force calculation. Shear force at A will be straight away equal to RA, that is 28 kilonewtons, and shear force at B, it will be RA only, and that is 28 kilonewtons at just a minute. Yeah, here the point has to be not B, instead it has to be C. This has to be C. So this is shear force at C and this is D. So shear force at C will be RA, that is 28 kilonewtons, and at C there will be sudden drop in shear force. It changes suddenly, that is 28 minus the point load is 24, which is 4 kilonewtons. Same way shear force at D will be 4 kilonewtons, and this suddenly changes to 4 minus 40, and that is minus 36 kilonewtons, and shear force at B, it will be minus 36 kilonewtons, and it suddenly changes to 0 as there is a reaction point reaction. So that is minus 36 plus 36, which is equal to 0. So let me just draw the shear force diagram. So shear force at A will be 28 kilonewtons, and it will continue this height is indicating 28 kilonewtons, and the shear force will be constant up till C, and from C onwards it is going to drop. So let me just extend the point C so that this will be up till C, and from here onwards the shear force is going to drop to 4 kilonewtons, and from here again the shear force is going to be constant, that is up till point D, that is up till point D. So let me just extend this line up till point D. So this is going to be up till point D. This was 28 kilonewtons, 28 kilonewtons. This would be 4 kilonewtons, and from here onwards, from point D onwards, it will drop and it will have a sign transition, and this will be 36. This will be 36. So let me just increase this height as it is going to be taking the maximum value, and it continues to remain constant for this duration, and at point B it becomes 0. So let me just draw the line. So at point B it becomes 0. This is 36 kilonewtons negative. This is positive. So now is the computation of bending moment. So bending moment at A will be 0 as it has got hinge support. So BM at A will be straight away equal to 0. Bending moment at B will be, that is BM subscript B will be at at C we need to calculate, because B is the free end or B is the roller support, so C needs to be calculated. So bending moment at C, it will be RA into distance between RA up till C, it's 2 meters. So RA into 2, RA it is 28 into 2, that is 56 kilonewton meter. Same way, bending moment at D will be, that is BM subscript D. So at D it will be RA into the distance between RA up till D is 6 meters, and along with that there will be point load at C which will produce counterclockwise movement, that is 24 into the distance is 4, and this is 28 into 6 minus 24 into 4. So 28 into 6 is 6 eights 48 it is. 6 twos 12. 12 plus 4 is 16. So this is 168 minus 96 it would be. So this will be 2, and this will be 9 minus 16 will be 7. This is 72 kilonewton meter. 28 into 2 it is. So next is bending moment at B, which is BM subscript B, which is RA into 8. The distance between RA up till B is 8 meters, and 20 up till from the point load 24 kilonewtons up till B is 6 meters. That is minus 24 into 6 minus of point load is 40, and up till B point it is 2 meters of distance. So RA is 28 into 8 minus 24 into 6, which is equal to 28 4s are 96, and 28 6 is 144, and this is minus 80. So this is 8 8s 64, and this is 8 2s 16. This is 224 minus 44 minus 80, and this will be equal to 0. So bending moment at the hinge and roller support will be 0. Just remember that. And now the bending moment at the bending moment diagram is to be drawn. So let me just draw the baseline. So this will be the baseline, and at A it is 0. At B it is also 0. So it is going to increase linearly as this is representing x power 0 line. This is x power 1 line, 0 line. It is still the x power 0 line, and even here also it is x power 0 line. So bending moment is going to be x power 1 line. So it is going to be continuous up till the point B. Up till the point B, the straight line will have the same slope up till the point B. Okay, so from this point onwards, the slope is going to change. The slope has to be modified because point load will produce the discontinuity. So let me extend this up till this line, and this diagram, let me take it little down. So this will be up till C. So just remember that all these points should be aligned properly. So that's when you make the easier for examiner to understand your calculations. At this was point C. This was point C, and this is point D, and bending moment at B we have calculated that as 0. So this would be 0. So you can see here the lines has got different slopes. Remember that and try to highlight that properly so that examiner knows you have the understanding of concept. So you can see here this was the line and this is another line. So these two lines are of different slopes. So the discontinuity has to be highlighted always. You can't say that it is going to be a same line and it will continue like that. That discontinuity highlighted shows your understanding of concept. This will be x power 1, this will be x power 1, this will be also x power 1 behavior. So for this problem you can avoid writing section xx and you can straight away solve the problem. So if you go for writing section xx, maybe you end up missing out any of the calculations. So that's not very important. The very important thing is you should be drawing the diagrams and supporting calculations should be expressed very neatly. So this was 56 kilonewton meter at C, and this has been computed as 72 kilonewton meter. So out of here we find that there is a sign transition from positive to negative, okay, at this location D, and that is when you are getting the maximum value. This is the maximum value of the bending moment. So the shear force, wherever the location the shear force changes the sign, that will give us the maximum value of bending moment. Just remember that. In the question, it says about a simply supported beam whose span is 5 meters and it is carrying a uniformly distributed load of 2 kilonewton per meter over the entire span, and a point load of 25 kilonewtons is placed at a distance of 2 meters from the left support. So this load is 25 kilonewtons and it is placed at a distance of 2 meters, and the height of UDL is 2 kilonewton, and that's distributed over 5 meter span, which means this would become 3 meters. So for this, a shear force and bending moment diagram is to be drawn. So first is, it starts with the computation of reaction forces. So here let's call this as point A, point B and point C. So at A there will be a hinge reaction due to hinge, that is in Y direction. Although you will be finding a reaction in X as well, but the reason is here X direction reaction will be 0. Reason, there is no force in the X direction, and there will be reaction in Y direction at point C as well. So summation of forces equal to 0 in Y direction. That's RA plus RC is equal to the point load of 25 kilonewtons plus area under the UDL. So UDL into length is 5. That's, so this is equal to RA is plus RC is equal to 25 plus 10. That's 35 kilonewtons. Next is bending moment at point A, that's equal to 0. So at A there will not be reactive movement because hinge is permitting the rotation. Hinge joint is going to permit the rotation, so that's why there will not be reactive movement minus MA, what we have seen in the cantilever beam. So here minus about A, RA is passing through point A, it will not produce any movement, but for UDL we need to write. So that's 2, it is distributed over 5 meters of length, and the UDL or UDL, when it is converted into point load, its location will be at 5 by 2 or midspan of UDL, I should say. So 2 into 5 into 5 by 2 plus 25 into 2, it would be minus RC into 5 it is, and this is equal to 0. So 2 5s 10 and 5 and this is 5 by 2 is 2.5. So 10 into 2.5 is 25 and 25 2s is 50. This is equal to 5 times of RC. This is equal to 0. So RC will be equal to, that's 75 by 5. So 75 by 5 is 15 kilonewtons. And here if we compute RA, so RA will be equal to 35 minus 15, which is 20 kilonewtons. So here you find that the reaction RA is nearby to the 25 kilonewton load, which means the RA is going to take maximum share from this 25 kilonewton load. Okay, that's why we are finding the value of RA greater than RC. Okay, and if it was UDL, for UDL the RA and RC will be taking equal shares. Now the computation of shear force at A is straight away equal to RA, that's 20 kilo. Next is shear force at section XX, let us say. Reason here is that we are finding the UDL distributed over entire span. So let me draw the section between the points A and B, and from point A up till section XX, let's mark that distance as X. So here we find RA force to be present, and along with that UDL of 2 kilonewtons over X meters of length. So when we convert UDL into shear force, it's 2 into X. We multiply or basically treat that as a rectangle whose height is 2 meters and the width or the length is X meters. So RA here, RA minus 2x. So here we find adjacent to x there is a negative sign or minus 2, which means the shear force is going to decrease. So shear force at point B, that is RA is 20 minus 2 into 2 it is. That is 20 minus 4 is 16 kilonewtons. And at point B, there is a additional point load of 25 kilonewtons. So that is going to produce sudden drop. Suddenly changes to 16 minus 25, which is minus 9 kilonewtons. And now if we go for the computation of shear force at point C, so shear force at C will be equal to, that is at B we have computed as 9, so minus 9 minus the portion of UDL between the points B and C, that is 2 into 3 meters. So as it is downward, that we will be taking it as negative, so minus 9 minus 2 into 3, so this is minus 15 kilonewtons. Next is at point C, there is a reaction RC present. So this reaction RC will definitely produce a sudden change as well. So this will be minus 15 and value of RC computed as plus 15. So this is equal to 0. So if we draw the shear force diagram for this situation, that is so shear force at A will be 20 kilonewtons. So I need to increase the height. This would be 20 kilonewtons. And from here onwards, we will find a linear drop up till point B. There is a linear drop. And let me check that if this is coinciding with point B or not. So this would be point B. and it decreases to 16 kilonewtons. Now at point B, there is a sudden drop in shear force because of the 25 kilonewton load, and that produces the transition in shear force sign, and it goes to minus 9 kilonewton. This is minus 9 kilonewtons, and same way from the minus 9 kilonewtons up till the point C, the shear force decreases to minus 15. So the slope of the line will remain same. That continues up till point C. And at point C, there is a sudden change to 0. From minus 15, it is becoming 0. So here we find that the reaction at C is having a greater height, so which needs to be corrected. Let me do that. So at C, we will be getting shear force as 15 kilonewtons. This will be negative sign, and this will be a positive sign. So just remember that here, if we placed even between B and C, if the shear force at section XX is placed, so what will happen? There is no change at all. That is, RA will be there minus 2 times of X, and along with that, the point load of 25 kilonewtons will also be added. So that is 20 minus 2x minus 25 it is. So this is basically minus 5 times of minus 5 minus 2x. So that is when the shear force is placed between B and C. SF at XX between B and C it is. So no need to worry about this. I mean, even if you are not doing this calculation. And next is the computation of bending moment. So computation of bending moment, that starts with the point A. Bending moment at A will be equal to 0, as RA is passing through the point, reaction RA is passing through the point A. It will produce 0 moment. And bending moment at B, if we compute, that's RA into perpendicular distance is 2, RA into 2 minus UDL, it would be the portion of UDL between A and B. That's 2 meters, that's 2 kilonewton per meter is the height of UDL, and it is between A and B, means it is distributed over 2 meters, and midpoint of that UDL between A and B is 2 by 2. That's 2 by 2. So this is RA, we have got it as 50. Sorry, it's 40, RA is 20, 20 into 2 is 40. So let me just correct this. Yeah, it's 40 minus 2 into 2 is 4, 4 into 1 is 4. So this is 40 minus 4, which is equal to 36 kilonewton meter would be the bending moment. Next is bending moment at point C if it is to be computed. So that will be 0 once again, but you can show it by calculation as well. So at C, that is distance between C and A is 5 meters. So RA is 4 for 20. RA is 20. 20 into 5 minus UDL will produce counterclockwise movement about point C. So UDL height is 2 meters. It's distributed over 5 meter span, and the midpoint it is going to act. The maximum UDL will be at the midpoint. That's 5 by 2 minus point load of 25 kilonewtons. It is at a distance of 3 meters. So 25 into 3. So let's check the calculation. So 20 into 5 is 100 minus 2 into 5 is 10. 10 into 1.5. This is 10 into 2.5, sorry, it's 25. 10 into 2.5 is 25 minus 25, 3s are 75. So this is equal to 0. So bending moment at point C will be 0. Next is the BM diagram. If we require to draw, then it is going to be a second degree curve. It's going to be a second degree curve. So now at bending moment at point A will be 0. It will be 0. This is A. And at point B, the bending moment will be maximum as the shear force is undergoing sign transition. So the location where shear force is undergoing sign transition, we get maximum value of the bending moment. So it is going to be a second degree curve parabola. So it will be maximum up till here, that is 36 kilonewton meter, and from point B onwards it is going to decrease parabolically up till from point B to C. It is going to decrease parabolically. So this would be the point C, and this is x power 2 behavior. This would be x power 1 behavior, and even this was also x power 1 behavior, and that is been reflected even in the SF equation, that is RA minus 2 times of x. RA is 20 minus 2x, so that is x power 1. So shear force is going to have x power 1 for the UDL, and for the bending moment it will be x power 2 behavior. So if we write bending moment about section XX, that is bending moment up to section XX, that is we find RA. Along with RA, there is UDL which is distributed for x meters of length. So RA is 20, x 20 into x minus UDL is height of UDL is 2, and UDL is distributed over x meters of length. So 2 into x, that is converted into shear force, and the midpoint of this is x by 2. So we would be getting an expression as 20x minus x square. So this is a x power 2 behavior. Bending moment is going to be x power 2 behavior for the UDL, and shear force will be x power 1 behavior. And since it is in horizontal line, so horizontal line we can call it as x power 0 behavior, or a constant line also. So that's how we can understand and build a pattern over here, how quickly the shear force BM and the loading diagram can be mapped very easily. In the question, it has been asked to develop the shear force and bending moment diagram. So here the load is being applied not at the center. It is eccentrically loaded. Let's name this point as C. So here first we start with computation of reactions. So there will be a reaction force that is in y direction and at the hinge support, and there will be a reaction force at the roller support as well. So two reactions in the y direction, and now summation of forces, that is RA plus RB, is equal to 30 kilonewtons. Next is computation of reactions, that is we are going to take the moments about the point A. This 30 kilonewton force is going to produce clockwise moment about the point A. So 30 into perpendicular distance is 4 minus the reaction at other point B is RB into perpendicular distance from A to B is 6 meters. And this is equated to 0. So RB here will be equal to 120 divided by 6, and this is equal to 20 kilonewtons, and RA will be equal to 30 minus 20, which is equal to 10 kilonewtons. Here also I want to tell you an observation. We are finding the 30 kilonewton force closer to RB. So the value of RB has to be greater than RA. Remember that. So that's when you can validate your answers, whether they are correct or not. So this is one of the ways. So you should always try to observe how far this applied load is from any of these reactions. So the reaction nearer to the loading point will be taking the maximum reactive force. Now let's do the computation of shear force. So shear force at A will be straight away equal to RA, that's 10 kilonewtons. Same way shear force at B, it will be still 10 kilonewtons, and at point, sorry, it has to be point C. So let me just correct this. It's 10 kilonewtons, and at point C we are finding a point load. So due to this point load, there has to be a sudden change of another 30 kilonewtons. So suddenly changes to 10 minus 30, and that is equal to minus 20 kilonewtons. Same way, shear force at B, it is equal to, that is minus 20, and at B we are finding the reaction force RA, that's minus 20 plus 20, which is equal to 0. So there is also sudden change at B. So now if we draw the shear force diagram, let us do that. So this will be the datum for the measuring of shear force. And first is that we have the shear force of 10 kilonewtons. It is distributed over a span of 4 meters. So we are finding this 10 kilonewton shear force over a span of 4 meters. So let me just correct it. So this I need to match it up till point C, it has to be. So this is the variation in shear force. So up till the span. And now the shear force at point C, we are finding it changing to minus 20 kilonewtons. So there has to be an increase in height of the shear force. So from C to B, it will be minus 20. And as we are dealing with point load, the shear force variation will be specified by the horizontal line. So this is the shear force at point B to C. So this is going to be 10 kilonewtons and it is positive. And here the shear force is negative and this is going to be 20 kilonewtons. Next, we can go with the computation of bending moment. So bending moment at A, it will be equal to 0. Bending moment at A, it is equal to 0. Reason is that at the hinge rotation is permitted, and even at the roller support the rotation is permitted. So bending moment at A will be 0 as RA is passing through the point A. So definitely the bending moment value will be 0. Next is bending moment at C, it is equal to RA into 4 meters. What is RA? RA is 10 into the distance is 4, that is 40 kilonewton meter. Same way, if we compute the bending moment at point B, then RA will produce clockwise moment, that is RA into 6 minus 30 into the distance between point C and B is 2 meters. So that is into 2. So this RA is equal to 10
10 into 6 minus 30 into 2, which is also 60. So bending moment at point B will come out as 0. So if we draw the bending moment diagram, so the bending moment diagram here at A and B, it will be 0, and it will be taking the maximum value at a location where shear force is either becoming 0 or it is going to experience the transition in sign or change in sign. Okay, so here it is going to have linear variation, and I'll elaborate this why the variation is a straight line. I'll elaborate by taking the section XX. So at point B to C onwards, again it drops and it becomes 0. So this would be the shear force diagram. Let me just realign it. Yeah. So this would be the shear force, and at point C, we are getting it as 40 kilonewton meter. This is BMD diagram, and this was the shear force diagram. So now if I take the bending moment about the section XX, let's say that this is the section XX, okay, and this is x dash. So here bending moment about section XX will be equal to RA, and the distance between section XX up till RA is x. So RA into x. So RA here it is 10 times of x. All right. And if we shift the section between the points C and B, okay, this was section between the points A and C. Same way, if we put the section between the points B and C, so let me just shift it over here. So if we shift this, the distance will be still counted as x. The distance between the reaction A and up till the section XX, it will be counted as x only. This would be distance x, and this is section XX. So now RA is at a distance of x from the section which is placed over here. So between point B and C. So RA, that is bending moment about section XX. So let's say this is the section we are going to count, which is marked in red color. So RA, that's 10 times of x, minus the distance between 30 and the section XX is x minus 4. That is 30 into x minus 4, it is power 1. So now we find that here if we try to solve this, this is 10x minus 30x plus 120. So this becomes minus 20x plus 120. So here we understand that the value of the slope previously, this is of the format y is equal to mx. So here the value of m was positive. So that is why you find here increasing slope. The slope was increasing. And same way here you find the negative value. This is a negative value. So the negative value indicates the decrease in slope. The slope here, it is still x power 1 behavior, and the slope will be decreasing. So this is also one of the standard problems you can go through. So we will be also making use the results of these of this problem in the extended concepts. So here in the question it is asked about drawing the shear force and bending moment diagram for the simply supported beam which is loaded with a point load at the center. So here remember that this is a standard case of a beam, and moreover the results obtained from this standard case will be utilized in the extended concepts of calculating bending stress, deflection, shear stress, shear force, all these will be extended. So please remember that what we are taking here is a standard result or standard case. So we will be seeing this standard result extended in other subjects as well once we progress into different parts of the design. So here we begin with, so first is that we are required to develop the shear force and bending moment diagram, which is loaded with a point load at the center. So let's call this as, here this will be a hinge support and there will be a roller support. So we can solve this problem by using symmetry, or we can also make use of equilibrium equations. So let's begin with equilibrium equations. Here summation of the forces in y direction, that's equal to 0. So Ra plus Rb equal to W, that is. So there will be a force at the hinge. Let's call this as Ra, reaction force, and there will be a force, reactive force at the roller support as well. So Ra plus Rb is equal to W. And next is, if we take the moments about A, that's equal to 0. So Ra is passing through point A, it will not produce any moment, and W is acting at a distance of L by 2. So W is producing clockwise moment about A, that is W into L by 2, minus Rb is producing counterclockwise movement about point A. So Rb into L it is, and that is equal to 0. So Rb we get straight away as W by 2, and Ra also it would be W by 2. So whenever you find a symmetrical loading, divide the total load by 2, and that total load will be shared by both the supports and they will be sharing equal amount of loads. So whenever we find a symmetry, we need to take an advantage of it. This is a case of symmetrical loading. So now let's begin the calculation of shear force. So here the shear force, first is shear force at point A is only Ra. That's Ra is equal to W by 2. It is positive. So let me just draw the shear force diagram. So here the force will be W by 2, that's positive upward force, and next would be